All right, isotopes. Atoms are defined by the number of protons in the nucleus. We have to have one number that represents that is the defining number because the other ones can change. So we use the number of protons. If it has 6 protons, it's carbon. That's how we define carbon. Carbon means 6 protons. Some atoms of carbon may have some different number of neutrons. So we have carbon 12, and that means that that carbon would have 6 protons, and this is the total number of protons and neutrons. So 12 minus 6, 6 neutrons. There's also carbon 14. Again, because it has 6 protons, that's how we defined it as carbon. The 14 here representing the total number of protons and neutrons. So if we take the 6 out of it, that means that this atom of carbon would have 8 neutrons. Atoms with an unusual number of neutrons are called isotopes. So isotopes for almost all the different atoms that we have exist, and so we can see that we don't always have a consistent number of protons. If we were able to isolate this, and we wanted to think about this in terms of the relative atomic mass, or the molar mass, we would discover that carbon 12 has a molar mass of 12 grams. If we could isolate enough carbon 14, we'd see that it has a molar mass of 14 grams. So isotopes have an unusual number of neutrons, and that unusual number of neutrons will affect the overall mass of the atom, and as a result, molar mass. This, all of a sudden, starts to help us understand why, on our periodic table, we have elements that have decimal points in their atomic mass. Copper is a good example here. Copper, what the heck is that? Copper has a molar mass of 63.55. Let's just go 63.5 to make the point. That doesn't mean that copper has a molar mass, or has 63 protons and neutrons plus 1/2. It doesn't mean that there's a proton or neutron here. Right? That doesn't make any sense. There's no such thing as half a proton or a neutron, or at least not within what we're talking about right now. So what does this really mean? Well, this means that copper might be made up of some copper 63 and copper 64. And when we take the average, we have to be careful here, the weighted average. So we take the average, taking into account what percentage of each of these things exist. That is what turned out to be 63.5. Now, it might not be just 63 and 64. Maybe there's a 65, maybe there's a 62, right? It depends on the atom, what isotopes exist. But when we take the weighted average of all of them, that's the number that you're seeing in the periodic table, and that's why there's a decimal place there. If we take something like lithium, for example, we can see that lithium is 92.5% lithium-7. So that is by far the most common. However, the rest of it is lithium-6. So using that, what is the actual atomic mass or molar mass for lithium? So we have to do a weighted average here. The molar mass for lithium is going to be equal to the percentage abundance, I don't know if that's spelled right, whatever, of an individual isotope. So for example here, okay, percent abundance of 6 times the molar mass of lithium 6 plus the percent abundance of 7 times the molar mass of lithium 7. So here, let's just do a little thing here. 92.5% of it is lithium 7, and all the rest is the other one. that means that 7.5% of it is lithium-6, right? So we had 100 minus the part that was 7, and that leaves us with that much for 6. So the percent abundance, 7.5%. Remember, whenever we use percents in equations, we always have to convert them over into their decimal place values, times the molar mass of lithium-6, which is just 6. It's not really 6. If you looked it up, it would be like 6.01 or something like that. But we'll just use 6 because, again, I like to round. Plus 92.5% converted to a decimal place times the molar mass of 7. Use my calculator here. I get the molar mass for lithium at 6.925 grams per mole. So taking into account the different isotopes of lithium, we don't get a molar mass of 7 because that's only some of them. We don't get a molar mass of 6 because that's not very many of them at all. That's some other percentage of them. If I weight it all out, I assume that my lithium is made up of a normal amount of lithium-6 and lithium-7, then I can get a mass that represents the average mole of lithium. So the atomic mass is equal to the percentage of isotope A times the mass of isotope A, plus the percentage of isotope B times the mass of isotope B, plus on and on and on and on. Let's do magnesium. So magnesium, the molar mass of magnesium, it's 78.7% magnesium 24. So again, I convert that into a decimal place, 787. And I'm just going to use 24 because that's close enough. Plus 10.13%, 0.1013, converted into a decimal, times my 25, plus, I'm just going to sneak down here so I can fit it in, 0.11117 times 26. Remember to go from a percent to a decimal in case you forget this. Can't imagine, but just in case, we're going to divide by 100 here. And so my weighted average for the mass of an average mole of magnesium works out to be, just punch it in my calculator here, 24.3 grams per mole. If you look on the periodic table, that's what you're going to get, and that's why. It's not that you have a third of a neutron or proton or whatever. It's that you really have all these things and they're all mixed together, so when you measure the mass, you're getting the average result of that, not the mass of any one of them. Alright, one more example here. Here we're going to figure out the percent abundance instead. So we're going to work backwards on this one. Boron is composed of boron 11 and boron 10. The average atomic mass of boron is 10.8. What is the percent abundance of each thing? So 10.8 is equal to, I'm going to use P for percent of 10 times 10 plus the percent of 11 times 11. Now I've got two variables here, so I can't solve this directly, but if I can come up with one more equation, I should be able to solve it. I'm giving you a second to think about that equation. Is that the percentage of 10 plus the percentage of 11 has to add up to what? That's right, 100%. So, P10 plus P11 adds up to 1. I'm going to use that. I'll solve for P10 for no apparent reason. So P10 is equal to 1 minus P11. And then if I substitute that over here, I can reduce my equation down into one variable. And then it will be solvable. So 10.8 is equal to distributing the 10 to both things, 10 minus 10 P11 plus 11 P11 try to minus it. 10 p's minus 11 p's, or plus 11 p's works out to be 1 p11, 10, and 10.8. So bringing the 10 over the other side, 0.8 equals p11. So 80% of my sample is p11. Coming over here, I can figure out then that leaves 20% of my sample to be P10. So we can use, if we knew the abundance, we can use it to come up with the average atomic mass. Or if we know what isotopes we have, we can use the average atomic mass to work backwards and figure out how abundant those individual elements are. Most importantly here, the reason we have these decimal places on the periodic table is not because we have half a proton or 9/10 of a proton or something like that in an atom, but it's because atoms come in different isotopes, and so when we average them out, sometimes we get decimal points.